Convolutional Neural Networks or CNNs. CNNs are deep learning models specifically designed for processing structured grid data, such as images. CNNs use convolutional layers that apply filters to the input image, capturing spatial hierarchies and features like edges, textures, and shapes. CNNs are widely used in computer vision tasks like image classification, object detection, and segmentation. Let's go ahead and implement this line by line in Python and understand convolutional neural networks. So I'm gonna already created a file here with which called cnns.py. I'm gonna first import the libraries. So first is TensorFlow STF. We'll be using TensorFlow, which is the main library for building and training deep learning models. We're gonna from TensorFlow.keras import layers and models. These modules within Keras with TensorFlow's high-level API for defining neural network layers and models. And then from TensorFlow Keras datasets, we're going to import MNIST. This imports the MNIST dataset from TensorFlow Keras datasets, which contains images of handwritten digits from 0 to 9. Let's go ahead and load and pre-process the MNIST dataset. So first, I'm going to say xtrain, ytrain, xtest, ytest. These two tuples are given to me from calling mnist.loadData. This loads the mnist dataset, splitting it into training and testing sets. Xtrain, ytrain are the training images and labels. Xtest and ytest are the testing images and labels. Next, I'm going to say xtrain, xtest is equal to xtrain divided by 255.0, xtest divided by 255 by 0. Here I'm normalizing the pixel values to a range of 0 to 1, improving the training process by scaling pixel intensity from 0 to 255 to 0 to 1. Next, xtrain equal to xtrain.reshape minus 1, 28, 28, 1. This reshapes xtrain to have a shape of number of samples, which is minus 1, 28, 28, 1. This reshaping prepares the data for the convolutional neural network, CNN in this case, where 28 by 28 is the image size and 1 represents the grayscale channel. Next, I'm going to say xtest equal to x underscore test dot reshape minus 1, 28, 28, 1. Similarly, reshapes the test data here. Now let's go ahead and define the CNN model. So first I'm going to say model equal to models sequential, and here I'm going to so what this does is it creates a sequential model where each layer is stacked in a particular sequence. So I'm going to write those in a particular sequence here. First, layers dot con 2d 32 comma 3 comma 3 comma activation equal to relu input shape equal to 28 comma 28 comma 1. This adds a 2D convolutional layer. Now in this 32 is the number of filters which are feature maps in the layer. 3 comma 3 is the size of the kernel that slides over the images to detect features. And then activation equal to relu. It applies the relu activation function to introduce non-linearity. Input underscore shape equal to 28 comma 28 comma 1. This specifies the input shape for the first layer. Next, I'm going to say layers dot max pooling 2d 2 comma 2. This adds a max pooling layer that reduces spatial dimensions by taking the maximum value in each 2 by 2 window, helping to downsample the feature maps and reduce computation. Next, I'm going to say layers.con 2d 64, 3, 3, activation relu. Now this looks familiar. This again adds another convolutional layer with 64 filters this time, a 3 by 3 kernel, and relu activation. Again, something similar. Layers max pooling 2d 2, 2. This again adds another max pooling layer to further reduce spatial dimension. Now, again, layers.con 2d 64 3 by 3 and activation relu. This again adds a third convolutional layer with 64 filters and relu activation. Then I'm calling layers.flatten. This flattens that 2D matrix from the last convolutional layer into a 1D vector, preparing it for the fully connected layers. So now I'm going to go and use dense layers.dense 64 activation relu. This fully connected dense layer with 64 neurons and ReLU activation. And then finally, layers.dense, comma 10 activation equal to softmax. This is the final output layer with 10 neurons, one for each digit class, which is 0 to 9, and softmax activation, which converts output into probabilities. Now let's go ahead, close it, and compile the model. So move it up a little bit. In here, I'm going to say model.compile optimizer Adam loss equal to sparse categorical cross entropy matrix equal to accuracy. This model.compile, it configures the model for training. Optimizer equal to Adam uses the Adam optimizer, which combines the benefits of adaptive learning rates and momentum. The loss equal to sparse categorical cross entropy sets the loss function to sparse categorical cross entropy, which is suitable for multi-class classification with integer labels. And then matrix equal to accuracy at the end tracks the accuracy during training and evaluation. Let's go ahead and train the model. Model.fit xtrain ytrain epochs equal to 5, batch size 64, validation split equal to 0.2. This function model.fit trains the model on the training data. X underscore train y underscore train, the training data and labels. Epochs equal to 5. The model will go through the entire training set 5 times. Batch size 64 updates the model after every 64 samples, improving computational efficiency. Validation split equal to 0.2 reserves 20% of the training data for validation, allowing the model to evaluate performance on unseen data during training. Now let's go ahead and evaluate the model. For that, I'm going to say test underscore loss, comma test underscore accuracy equal to model dot evaluate x test y test. This evaluates the model on the test data and returns the loss and accuracy. X underscore test, y underscore test are the test data set and labels. Test underscore loss is the final loss on the test set, and test underscore ACC is the accuracy achieved by the model on the test set. Let's go and print the test accuracy, indicating how well the model generalizes to unseen data. Let's save it and go ahead and run it. I'm going to call it python cnns.py. It's going to take some time because I'm going to run 5 epochs, which means it's going to go through the data set 5 times. So I'm going to just fast forward this part to the last. So we are in the last epoch here, almost training with all the 750. And there you go. We have our test accuracy. It is 0.988, which means almost 99% since 98.8. So it's pretty good. So as you can see, using the data set that we had, we trained this model and created a model that can kind of read handwritten numbers and tell us what number it is. So I hope you were able to follow along building this CNN algorithm. And if you had any issues, any problems, or have any questions, let me know and I'll get back to you.